All right. Good morning, everybody. Welcome back. So for today, let's continue talking about thermochemistry. Um, and I will show you today another way to determine the delta H for a chemical reaction. All right. Let's see where we stopped here. Yes, it's Friday. It's exciting. Okay. All right. So for today, uh, we need to talk about enthalpy of formation. We are going to use enthalpy of formation to determine the delta H of any chemical reaction. The enthalpy of formation symbol is delta H F of a substance is the standard reaction enthalpy per mole of formula units for the formation of a substance from its elements in their most stable form. Okay, so what does that mean? Usually, when we have a reaction that starts with simple substance formed by the elements that are part of the final compound, we say that the reaction is correlated to the enthalpy of formation. And here, simple substance is defined as a substance formed by one kind of element. So the first example that I want to show you here is the formation of water molecule. The water molecule is composed by hydrogen and oxygen. Therefore, the reaction that describes the enthalpy of formation for water starts with hydrogen gas, okay? So one of the elements that forms water, plus oxygen gas, which is the other element that forms the water molecule. So therefore, we are starting with only simple substances, and the only product is uh, a complex substance or a substance that's formed by more than one element. Therefore, when we have this kind of reaction, we are determining the enthalpy of formation for water. At this point, I would like to draw the energy diagrams and show you some things, and then I will give you a second concept for the meaning of enthalpy of formation, okay? So now let's work on the energy diagram for this reaction. Let me change to my other screen here really quick. Okay, so let's write some things here and let's see if this is more clear. Okay, so again, we must start with simple substances, which are substances formed by only one kind of element, and the only product has to be a complex substance. Okay, so by definition, the energy of a simple substance is always zero. Okay, so let's note this here. The energy of a simple substance is always equals to zero. So looking at the reaction, now let's identify if any of the components of the reaction is or are simple substances. So starting here with hydrogen gas is formed by hydrogen bonded to hydrogen, therefore one kind of element, which means simple substance. Therefore, the energy for hydrogen gas by definition is zero. So let me mark here that hydrogen is a simple substance. The second component of this reaction is oxygen gas, which is oxygen bonded to oxygen, therefore a simple substance as well, because it is formed by only one kind of element. Okay, so see here that all the reagents are simple substances, and therefore, by definition, the energy of simple substances is zero. If we draw our energy diagram, let's mark here energy in kilojoules per mole, because that's the unit here. The energy level of the reagents is going to be zero, because both reagents are simple substances. And that's going to be our starting point in the energy diagram. So I'm going to mark here zero. Reagents are hydrogen gas and half of oxygen gas. Okay, so with that, we have a starting point, zero, which is the enthalpy of the reagents. The reaction will proceed, and the only product formed is water. Water is not a simple substance, therefore, the enthalpy of formation for water is going to be different from zero. And we know from the problem that the delta H of the reaction is negative, therefore, the reaction is exothermic. So therefore, the reaction will proceed to a lower energy level, and the only product formed is water in the liquid state. And here we don't know the energy level for the products. However, we know that the delta H, which is the difference between energy of the reagents and energy of the products, is minus 286 kilojoules per mole. Okay, so we know that we are starting from zero because we only have simple substances, and by definition, the energy of a simple substance is zero. We are moving to a lower energy level because the reaction is exothermic, and forming only one product, which is water, that we don't know the energy of the product, but we know that the delta, the difference between final and start, is minus 286 kilojoules per mole. So now what I'm going to write is that delta H, when we have a delta, that means we always have the final enthalpy of the products minus the start enthalpy of the reagents. Enthalpy means the energy level of products and reagents. Well, we don't know the final energy level, and I'm going to call the final energy level as delta H of formation for water minus the energy level of the reagents. Because we only have simple substances, the energy level of the reagents is going to be zero. Okay. And again, here, this is zero because we only have simple substances to start with. Okay, so can you see that the delta H of this reaction is going to be exactly the delta H of formation for the water molecule in the liquid state. And delta H of formation, you can see as the energy that the compound carries to other reactions. It's like an energy pack kind of thing. We are determining exactly the energy for that compound. Replacing the numbers here, we have delta H of formation for the water molecule in the liquid state equals to minus 286 kilojoules per mole. So therefore, the energy of 1 mole of molecules of water in the liquid state is minus 286 kilojoules per mole. Okay, so the water molecule is going to carry this energy pack to other reactions. And that is the idea of enthalpy of formation, is how much energy the molecule has, kind of. Remember here that a simple substance always has energy equals to zero by definition. If you start building first the energy diagram, looking at what you have, then the next step is to determine the enthalpy of formation of your product, which is going to be a complex substance. Okay, so this example was the formation of water, starting from simple substance, hydrogen and oxygen. The only product has to be water in the liquid state, and we determined the enthalpy of formation for water, which is minus 286 kilojoules per mole. And that's, you can see it as the energy of one water molecule, 1 mole of water molecules in the liquid state. Okay, so now I want to show you a second example, and the one I like to do with you is this second reaction here because it's an endothermic reaction opposed to the first one, which was an exothermic reaction. Okay, so I'm not going to do the example on the top because it's the same idea as the first one. So let's tackle here the second reaction. Okay, so here again, we are starting with nitrogen gas reacting with oxygen gas, and the only compound that's being formed is nitrogen monoxide in the gas state. And we know that the delta H for this reaction is 90 kilojoules per mole. Okay, so that's called the formation of nitrogen monoxide reaction. So we always start identifying if there are simple substances. Remember that a simple substance is a substance formed by only one kind of element. In this case, we have here nitrogen is a simple substance, and also oxygen is a simple substance. What is the importance to find the simple substance? Well, the simple substances, by definition, have energy equals to 0. Okay? Therefore, all the reagents here, the energy level for them is 0 because they are simple substances. With that, we can start drawing the energy diagram. So let's go here. Always try to do a good work here. Don't do a sloppy work. So we have here energy in kilojoules per mole because that's the unit being represented here. The first point that we know from this energy diagram is the energy level for the reagents, which is 0. So let me draw here. That's the energy level for the reagents. And we have here half of nitrogen gas reacting with half of oxygen gas. The reaction will proceed. The only product formed is nitrogen monoxide, and the goal here is to determine the energy level for the only product. Because the delta H is positive, that means the reaction is endothermic. As a consequence, the energy level for the product is going to be higher than the energy level of the reagents. Okay, remember that an endothermic reaction absorbs energy from the neighborhood, moving the energy level up. And the only product that we are forming here is nitrogen monoxide gas. We don't know the ending point of the energy, but we know that the delta H, which is always the difference between energy of the reagents related, energy of the products related to the reagents, in this case is equals to plus 90 kilojoules per mole. So our goal here is going to be the determination of the top energy level, which is the energy of 1 mole of nitrogen monoxide molecules. So the next step is to use the formula for delta H. Delta always means final minus initial. For a chemical reaction, products minus reagents. The enthalpy of the products we don't know, and I'm going to call here that this is the enthalpy of formation for nitrogen monoxide in the gas state. And we know that the enthalpy of the reagents is 0 because they are all simple substances. Okay.
Wait, I have a question.
Yes.
So how did you determine that the energy level was 0 again?
Okay. So by definition, okay, so this is a definition. Uh, the energy of a simple substance is always 0. So
Oh,
if,
okay.
okay, so if you look at hydrogen, because it's only one atom, you basically react two atoms of hydrogen and form one molecule of H2. Because no bonds were broken, the definition is that the energy of the simple substance is going to be 0. Okay?
Okay, yeah, thank you.
Yes, no problem. Okay, so if you think about the reagents will provide the level that the energy of the product is going to be compared. Okay, and that's why the definition is 0 because it's just more convenient. Okay, so now let's replace all the numbers that we have here. We have the delta H of the reaction, which is 90 kilojoules per mole. And the only thing that's left on the right side of the reaction is the enthalpy of formation for nitrogen monoxide gas. Okay. So therefore, you don't have to do any other operation. So with that, we determined the energy level of the only product, which is plus 90 kilojoules per mole. So that means the energy of 1 mole of nitrogen monoxide molecules is 90 kilojoules per mole. That's the energy pack that a NO molecule carries to any other chemical reaction. So therefore, using the formation reactions, we can determine the energy of any molecule. And that's what I showed you here. We are always going to identify who are the simple substances because those have energy equals to 0. Start drawing the energy diagram, see if the reaction is moving up or down. Mark the delta H, write the delta H formula, and then from there you can extract the delta H of formation for the compound that's being formed. Okay, so now let me show you how you're going to use the delta age of formation for each chemical substance to help you find the delta age for any chemical reaction. So let's do here an exercise. If an engine is not working correctly, fuel combustion will generate carbon monoxide instead of carbon dioxide. Using the data from the table below and the balanced equations, calculate the delta H for the incomplete and complete combustion of methane. So the first reaction shows the incomplete combustion. When we have incomplete combustion, we don't have enough oxygen to burn the fuel, and one of the products formed is going to be carbon monoxide and water. And the second reaction shows the complete combustion. When we have excess of oxygen, all the fuel is burned and converted to carbon dioxide and water. We are going to use the delta age of formation for each compound involved in the reaction to determine the delta age for both reactions. Okay. So remember that the delta age of formation is basically the energy of that molecule. One thing that you should pay attention to is that enthalpy of formation is going to be always in kilojoules per mole. Therefore, it depends on the amount of substance. Any unit that is divided by mole depends on the amount of substance. Therefore, if we read the first row, each mole of carbon dioxide has an energy of minus 393.5. If you have two, of course, you have to double, and if you have three, you have to triple, okay? See, Emmanuel, the difference between only using kilojoules or kilojoules per mole. When you use kilojoules per mole, you are saying that for each mole, that's the energy. And therefore, it will depend on the amount of substance. Okay, so let's start tackling the first reaction, which is the incomplete combustion. So it is right here. So let's see how we can use the delta age of formation to help us to extract the delta age for the reaction. So our goal here is to determine the delta age for the incomplete combustion first. Always start looking at the reaction and identifying if there are simple substances. Remember that a simple substance is a substance formed by only one kind of element. CH4 is not a simple substance because it's formed by carbon and hydrogen. However, oxygen is a simple substance. What's the importance of finding the simple substances? Because by definition, the energy of a simple substance is always zero. Okay? Carbon monoxide, not a simple substance, and water is not a simple substance as well. So now what I'm going to do is to draw the energy diagram for this reaction and determine the energy level for reagents and products using the delta age of formation for each of the compounds involved in the reaction. So let's start with the reagents. So this is what we are going to do here. The energy of the reagents is going to be 1 times. We are going to use the delta age of formation for methane, because that's the energy of 1 mole of molecules of methane. From the table, that's minus 74.8 plus the energy of 3/2 of oxygen molecule, which is 0. And we are going to do the same thing on the product side. Okay. So we are going to determine the energy level of the products from the delta age of formation. Starting with carbon monoxide, 1 mole of carbon monoxide. Each carbon monoxide carries an energy of minus 110.5. This is from the table here. Plus, we have 2 water molecules in the liquid state, and each water molecule carries an energy of minus 285.8 kilojoules per mole. Therefore, let's do the operations here. The energy level of the reagents is going to be minus 74.8 kilojoules per mole. And the energy level of the products is going to be minus 682.1 kilojoules per mole. Okay, so using the delta age of formation, which is the energy of 1 mole of molecules, we can determine the energy level for reagents and products. With that, now we can build the energy diagram for this reaction. So we are starting here at minus 74.8. The reagents are methane and 3/2 of oxygen. And see here that the energy level of the products is lower than the energy level of the reagents. So we are going to move all the way down to minus 682.1 CO gas and 2 water molecules. So therefore, the reaction moves to a lower energy level, which means this reaction is exothermic. Well, every time you burn something, energy is going to be produced. Therefore, any combustion reaction must be exothermic. And that's what we found here using the delta age of formation. At this point, the problem is not solved yet, but it's very close to the end. So right now, our goal is to determine the delta age, which is the difference between energy of products and reagents. Delta is always final minus initial. Let's replace the numbers. Enthalpy of the products is the energy level of the products. Don't forget the sign. Minus, attention here, energy level of the reagents, which is minus 74.8. Therefore, the delta H for the incomplete combustion of methane is going to be minus 607.3 kilojoules per mole. Therefore, for each mole of methane that reacts with 3.5 moles of oxygen, the amount of energy produced is 607.3 kilojoules. And that's how we are going to use the enthalpy of formation for each of the components in the reaction to determine the delta H of the global reaction. That was the calculation for the incomplete combustion. Now the next step for the exercise is to do the same thing for the complete combustion. So let's do that after a minute. Okay, so now let's look at the complete combustion reaction. The biggest difference here now is that we have more oxygen reacting, and as a consequence, carbon dioxide is going to be formed instead of carbon monoxide. So let's see what is the effect of that on the delta H. So the goal here, again, is to determine the delta H for this reaction. Always start looking for simple substances in the equation. Again, the only simple substance for this reaction is oxygen. The importance of finding simple substances is that you know that the energy of that compound has to be zero. And I'm going to follow a similar strategy that I used for the first case. So we are going to determine the energy level of reagents first, using the enthalpy of formation for each compound. So let's start here with methane. Remember that we need to consider the amount of substance that we have in the reaction. For methane, we just have one. Enthalpy of formation, according to the table, is minus 74.8, plus we have two oxygens, and we know that the enthalpy of formation for oxygen is 0 because that is a simple substance. Therefore, the energy level for the reagents is still minus 74.8 kilojoules per mole. And we are going to do the same thing for the product side of the reaction. So let's determine the energy level for all these people here. Starting here with CO2, only have one CO2. Now look at the difference of the enthalpy of formation for CO2 compared with carbon monoxide. Now we go all the way down to minus 393.5 plus 2 times the enthalpy of formation for the water, minus 285.8. Therefore, the total energy for the products is going to be minus 965.1 kilojoules per mole. Now that we know the energy level for reagents and products, let's draw the energy diagram for this transformation. We have here energy in kilojoules per mole. We started the reaction with methane and 2 moles of oxygen. We know that the energy level is minus 74.8 from the enthalpy of formation. And see that the reaction now goes all the way down to minus 965.1. The products are going to be carbon dioxide and water. And we also know the energy level. And we know the direction of the reaction all the way down. Okay? Therefore, this is an exothermic reaction. Again, combustion always produce energy. Therefore, any combustion reaction has to be exothermic. And at this point, we are almost at the end. The only thing left here is to determine the delta H. Now that you know energy level of reagents and products, the calculation of the delta H is very simple. Energy of the products minus energy of the reagents. Energy of the products is 965.1 minus energy of the reagents minus 74.8. Okay, just be careful here with the signs. Minus with minus will become plus. Therefore, the enthalpy for the complete combustion reaction is minus 890.3 kilojoules per mole. Okay. See that the difference between complete and incomplete combustion is basically the amount of oxygen that is reacting, and the consequence of that is the production of CO2 instead CO. But that has a huge effect in the final value of delta H. So if we compare here, minus 890 with minus 600. That's almost 50% more. So what is the practical consequence of that? If the engine is not regulated, the amount of oxygen that goes in the combustion chamber is going to be less than ideal. That will produce incomplete combustion and produce less energy. Well, if less energy is produced, you have to spend more fuel. Therefore, engines that are not regulated properly, they will be less fuel efficient, also produce carbon monoxide. Carbon monoxide bonds to one of the proteins that transport oxygen, and that will block the transport of oxygen in your body as well. Okay, so therefore, make sure the engine is properly regulated to avoid incomplete combustion. And that's how you can use delta age of formation to determine the delta age of any chemical reaction. So that's a good point. Oops. That's a good point to stop for today. And with that,